everybody, welcome back to the channel. This video is going to be very short actually because the law of conservation of mass only takes up 2 slides in this PowerPoint presentation. The type of conservation of mass that we cover is going to be very basic relative to the type of law of conservation of mass chemistry that you can do in an upper level class. We are going to do a lab that hopefully would get you kind of familiar with the idea of stoichiometry, which is the more advanced stuff of this. However, we're just going to focus more on the very basic. So what is the law of conservation of mass and how can we use it in problems? So chemistry in the scheme of all of science is actually a relatively new branch of science, and that's because we need a lot of equipment in order to study chemistry. We need scales, we need thermometers, we need lots of different pieces of glassware. So something as simple as the law of conservation of mass really only came to light back in the late 1790s. And in relation to physics and biology and even astronomy, that's very late in terms of a lot of the other branches of science. But anyway, back in the 1790s, chemists were revolutionizing the scientific world, and that's because they were having advancements using new pieces of equipment. And because of that, they were able to quantitatively, using numbers, analyze chemical reactions. And this new advancement of science using quantitative measurements, we were able to determine lots of new information about chemical reactions that we never knew before. And therefore, at this time period, we were able to discover one of the most basic laws in all of chemistry. And this law is the law of conservation of mass. And the law of conservation of mass says that mass is neither created nor destroyed during ordinary chemical reactions or chemical changes. So you can't lose mass and you can't gain mass in a regular chemical reaction. Now, the reason why I say ordinary or regular is that your nuclear reactions, you tend to have loss of mass when particles come together. Most of the chemical reactions that any chemist would encounter, mass will always be conserved, which means the mass that goes in is equal to the mass that comes out. So here's a very basic picture. So in this case, we have sulfur, that's in this first test tube right here, reacts with iron. And it looks like I have 32 grams of sulfur that's reacting with 56 grams of iron. Those are my reactants. In this particular equation, when you add these together and heat them, you will form a totally new substance, and therefore the mass of the product will equal 88 grams. And that's because 32 grams of sulfur plus 56 grams of iron will produce 88 grams of product. Of course, that's assuming that all of the reactants react, but again, that's something we're not going to get into. That's the law of conservation of mass. What goes in, the mass that goes into a reaction must equal the mass that comes out. So 32 grams of sulfur and 56 grams of iron will react to form 88 grams of iron to sulfide. That's the law of conservation of mass. Here's another one. So in this case, I have 50 grams of calcium, and I'm reacting that with 150 grams of zinc carbonate. And this is an aqueous solution. That means that it's dissolved in water. So I have 50 grams plus 150 grams. I have 200 grams of my reactants. So again, that's on the left side of the arrow. Anything that's on the left side is always a reactant. If I have 200 grams in my reactants, I must also have 200 grams in my products, because the law of conservation of mass says that the mass that goes in the reactants must equal the mass that comes out in the products. So if I have 125 grams of calcium carbonate that was produced, you should be able to produce 75 grams of zinc because 125 plus 75 gives you 200. That's literally it, the law of conservation of mass. That's really as deep into this as we are going to get. Let's just do some example problems with this. And these are more word problems, so we're going to walk through these, but I'm going to switch over to the note packet now, and we're going to work through these together. So sample problem 4. A student heats 1 gram of a blue compound and obtains 0.64 grams of a white compound, as well as an unknown amount of a colorless gas. How much gas did the student obtain? When you do problems like this, especially if it's a word problem, my biggest advice is to always write down what you're given in some sort of an equation. I think it allows for you to see these a little bit better. So I'm going to try my best to write this out here. So I have 1 gram of some blue compound. So I'm just going to write blue compound. And we're heating it up. And when I heat this up, I'm obtaining some white compound as well as a gas. So I have a blue compound, I heat it up. Normally to represent heat in a reaction, you draw a little triangle above it. It's a little fun fact for you. That blue compound, I heat it up and I get a white compound as well as a gas. So let's go ahead and write our numbers in. Let's pick a different color here. Let's pick blue because we're working with blue. I have 1 gram of this blue compound. And when I heat that up, the student's obtaining 0.64 grams of a white compound. And they're also producing some amount of a gas. And we want to know how much gas did the student obtain. What you need to look at is the sum of the reactants and products. So on your reactant side, you only have 1 reactant. Therefore, you have to also have 1 gram of reactants coming out. So this has to equal 1 gram, which it does. So what plus 0.64 grams gives us 1? Answer should be 0.36. So your answer is 0.36 grams because the sum of your products must equal the sum of your reactants. So 1 gram on this side and 1 gram on this side. Let's try B. When 245 grams of potassium chlorate is heated, the potassium chlorate breaks down into potassium, chlorine, and some oxygen. What is the mass of the oxygen that's formed? So we're starting off with this potassium chlorate. And what's happening is we're taking that potassium chlorate and I'm heating it up again. So if you wanted, you can draw that little triangle. And when you do that, you're going to produce some potassium. I'm just going to write symbols for these. We're producing chlorine and we're producing oxygen. And this is not the correct formula for anything, but we really don't need formulas to figure this out. So let's pick a different color again. Stick with blue, I guess. So we have 245 grams of potassium chlorate. We heat it up, we break it down. We have 78 grams of potassium that's produced, 71 grams of chlorine, and we want to know how many grams of oxygen. Again, compare your reactants to your products. So I only have 1 reactant here, and that 1 reactant is the 245. So therefore, all of my products must also equal 245 grams. So this is 245, and this is 245. So 78 plus 71 plus what gives you 245? The answer should be 96. So I'll just draw right over that. 96 grams. You would produce 96 grams from this because the law of conservation of mass says that what goes in must equal what comes out on the product side. And lastly, let's try C. So C, a reaction between sodium hydroxide and hydrogen chloride gas yields is a fancy word for like produces or makes, or chemists like to use fancy words. So they typically use the word yields, sodium chloride and water. And then we start getting all the numbers here. What I'm going to do first is I'm just going to write a reaction out for this because, again, I think it's easier to take these word problems and to write out an equation because it's easier to kind of digest all of the information the problem is giving you. So we have sodium hydroxide, and that's reacting with hydrogen chloride, and I'm producing sodium chloride and water. So here's my reaction. Sodium hydroxide reacts with hydrogen chloride, and we produce or yield sodium chloride and water. Let's write our numbers in next. So a reaction with 22.85 grams of sodium hydroxide and 20.82 grams of hydrogen chloride gives off 10.29 grams of water. So we want to know what's the mass of sodium chloride that's formed. Here, I don't have just one reactant or product, so you do have to add the total for each of these. So let's go ahead and do that. I have my reactant side, and we have our product side. Since we have both of our reactants, let's find the sum of these two. I have 43.67 grams of reactants total. That means that I must also produce 43.67 grams of products, because that's what the law of conservation of mass said. Mass is conserved in a chemical reaction. I can't lose or gain anything new as a result of this. So what plus 10.29 gives me 43.67? You do a little subtraction there, and you should find that you should produce 33.38 grams of sodium chloride as a result. And that's because 33.38 grams of sodium chloride reacts with 10.29 grams of water to give us 43.67 grams of products, which must be produced because 43.67 grams of reactants are being used up in this equation. That's the whole very basic idea behind the law of conservation of mass. For us, it's really not going to get more complex than this. You might have to draw a reaction out, kind of similar to C, but otherwise, that's about it. You would only get more in depth with this if you were getting into Chem II, which is actually the first unit we start off with, which is stoichiometry. So if you have any questions on this, make sure you let me know. We're not going to get too much practice with this in class because I do think this is a pretty self-explanatory idea, but this lends very well into our next section of this unit, which is all about balancing chemical equations. So we're going to do that next, right after we finish law of conservation of mass. I will see you in the next video. Bye.